Welcome. And this is our webinar on PFAS treatment for drinking water utilities. My name is Steve Green. I'm Chief Commercial Officer of ATEC Water Systems, and I'll be the webinar host here today. We'll start with introductions of the panelists, and then I'll go over a regulations overview for PFAS. Then Lee Odell will go over treatment options for PFAS. Matt Geary with Setco will then go over surface modified clays for PFAS absorption. We intend to leave about 15 minutes at the end for questions and answers. You should see a question and answer portal. I believe it's at the top of your screen. And you can type in your questions at any time. We will address those at the end. So feel free to type those in as you have questions. So again, my name is Steve Green, Chief Commercial Officer with ATEC Water. I've spent about my 25-year career in the water industry, starting out as a consulting engineer, helping water utilities with infrastructure upgrades, both conveyance and treatment, before pivoting into the technology side of the industry, working at companies such as Xylem, Amniod Filtration, Water Tectonics, and others. So I've dedicated my entire career to helping water utilities understand and implement technologies that keep their water safe and available. Lee Odell is the Chief Operating Officer of ATEC Water. Lee has also spent his entire career in the water industry, working at businesses such as Setco, sorry, not Setco, Jacobs, Consor, CH2M Hill, and even had his own business, Odell Engineering. Again, helping utilities with water infrastructure upgrades, and his focus on water treatments. Matt Geary is the Technical Sales Manager of Environmental Products for Setco. Matt has spent quite a few years in the industry and is a specialist in absorption technologies and has been focused on PFAS for quite a few years now. ATEC Systems, we build water treatment systems for groundwater utilities. Our business started in the early 80s with a focus on agricultural irrigation filters. The business then pivoted to focus entirely on groundwater treatment for water utilities in about the mid-90s. The business was then purchased from the original owners in about 2022 by Cadiz. Cadiz is a private water wholesaler based in California that is developing a system that'll develop and deliver water to utilities in that region of Los Angeles. In 2024, we are delivering a record system for our business that addresses about 60 MGD of groundwater for the Central Utah Water Conservancy District in Utah. And also in 2024, we've signed this partnership agreement with Setco, where we will be supplying their absorption technology for PFAS applications for drinking water utilities. And that is really the reason for this webinar here today, is just to introduce this new partnership, talk about the various treatment technologies available for PFAS, and a little bit extra focus on the surface modified clays that are manufactured by Setco. So here at ATEC, we address all types of groundwater contaminants, PFAS obviously being one of those. We address flow ranges anywhere from 10 gallons a minute, campgrounds, small HOAs, all the way up to large utilities, as much as 100 MGD. Matt, I'll let you give a brief intro to Setco and Minerals Technology.
Thank you. And thank you everyone for joining us today, and a special thanks to the ATEC folks for putting this together. So as Steve had mentioned, I'll be going fairly in depth into the FLUOROSORB absorptive media, but it probably makes sense to introduce a little bit about the parent company, which is Minerals Technology, Inc. Minerals Technology Inc. is a minerals mining company, and that will become a relevant fact as we get into talking about the focus product here today. Minerals Technologies is cordoned into 4 different groups. There's consumer and specialties groups, making makeup products and kitty litter, specialty additives for paints and toothpaste and medical. On the top right is engineered solutions, which are mostly high temperature technologies, high temperature clays. And where Fluorsorb sits is that bottom right segment, the environment and infrastructure. And that's what we'll be talking about in just a few minutes.
Great, thanks, Matt. Appreciate it. Okay, so, oops. So overview of PFAS and regulations, just real quick to set the context here. So the PFAS compounds have been around since approximately 1938, used in a lot of different products that we use in our daily lives. Initially, there was a lot of focus to use it as a firefighting foam, waterproofing, things like that. And so a lot of the initial pollution stemming out of PFAS came from a compound called AFFF, which was used in a firefighting foam, which is something very essential to deal with fires that could occur places such as airports that are fueled by hydrocarbons. Those are hard to extinguish. And so it's been a great technology that's helped to keep us all safe. Unfortunately, a lot of unintended consequences. It does not break down readily in the environment. And so a lot of that, those compounds have migrated into our groundwater sources. Initially, it appeared that a lot of the pollution would be limited to areas where there were airports or military bases where there was a lot of practicing done or actual firefighting done with that AFFF. But as time has gone by, and these compounds have been used more broadly in personal care products, clothing, right, all sorts of applications. Really, turning out that the pollution is really occurring anywhere there's urban land use. So it's an issue that's going to be here for quite some time to come. The good news, though, is that there are some good technologies to address PFAS and remove it from groundwaters, which we'll go into more detail about here today. So since April of this year, these compounds are officially regulated by the EPA across all the states. Prior to that, some states had adopted their own regulations for PFAS, and there are some different levels in particular states, but by and large, right, it's driven by the EPA. So between now and 2027, water utilities are required to monitor and inform the public of whatever levels of PFAS compounds that they detect. By 2029, if they are over the MCL, which is the maximum contaminant level, which is an enforceable level by the EPA, then you have to notify your customers, right, of that water utility. 2029 onwards, action is required, which means you do have to implement treatments and notify the public. What we are seeing, most utilities we're working with currently, once they know they're at or near or over that MCL, they are moving forward with treatment about as soon as they can get it in place. Obviously, there are health risks associated with PFAS. And so, once people know that's in their water, they tend to want their utility to address that right away. As far as where PFAS is occurring, again, initially it was believed this would be isolated more to areas where you had airports, military bases, or some sort of industrial pollution. As more and more wells have been sampled, that's enabled the ability to basically model where these contaminants will occur. So the USGS recently undertook that effort and published the results. You can see that here on the slide. There's a color-coded likelihood of occurrence, and essentially that's been correlated to urban land use. So most likely where there's population centers that use groundwater as their source, right, there is going to be a need to treat for PFAS. So treatment options for PFAS removal from groundwater. We'll turn it over to Lee Odell to focus on this section. Go ahead, Lee.
Thanks, Steve. You can go ahead and go to the next slide. So there's a number of different treatment approaches that are sort of been talked about and are in use for other aspects of destroying PFAS. But for drinking water treatment, there's really 4 commercially available options. One is ion exchange, and normally that's run as adsorptive media and replaced periodically. There's activated carbon, which absorbs PFAS compounds. The modified clay absorbent Fluorosorb that we're talking about today, and high pressure membranes like reverse osmosis. Go ahead and flip to the next one. So this is kind of a little comparison of those 4 options. For ion exchange, it's good for short and long chain PFAS compounds. The type of runs that you get before you have to replace or regenerate the media varies significantly depending on the type of resin and a little bit of water quality as well. Pre-treatment's required for all of these adsorptive type treatment projects or treatment applications. We don't want to backwash them. Backwashing them stirs up the media and shortens the time to breakthrough. So pre-treatment's very important for all of these options. Getting particles out of the water that are less than 10 microns, making sure you have iron and manganese removed before the PFAS treatment, all will help extend the time that the resin can continue to remove PFAS compounds. The design criteria for ion exchange is pretty short. So typically 2 to 3 minutes of empty bed contact times with a lead and a lag stage. It will work very well. Capital costs generally are low. The resins themselves can be fairly expensive, so the change out time can be a major factor in the life cycle cost and the cost of changing that out. Operations pretty simple. Disposing of the residuals typically get incinerated or landfilled. With granular activated carbon, they're better for long chain PFAS compounds, but they can remove short chains. They just tend to break through quicker. The number of bed volumes is a little lower, but you have bigger tanks. So pre-treatment's very important, but longer empty bed contact times are required for granular activated carbon, typically 10 minutes and a lead and a lag stage for a total of 20 minutes of contact time. So the capital cost is a little higher because the tanks are bigger. We got more media. The replacement frequency, again, plays a major role in the life cycle cost. They're easy to operate. The media can be reactivated and sometimes reused, but sometimes you'll build up compounds that have other things in the water, so you can't necessarily reuse the granular activated carbon for too long. With Fluorosorb, it's good for both long and short chain PFAS compounds. You tend to get very long runs to break through with the Fluorosorb compounds. Pre-treatment, again, very important, but the tank approach is more similar to ion exchange. So the ion exchange and Fluorosorb, you might think of as the small tank approach, just 2 minutes, 2 to 3 minutes of empty bed contact time, a lead and a lag stage for both ion exchange and for Fluorosorb. The cost of Fluorosorb is lower than the cost of ion exchange resin, so it has an overall lowest capital cost. You get good long runs with it, which often makes it the lowest life cycle cost as well. Very easy to operate, and the residuals are typically landfilled. With high pressure membranes, we're talking about reverse osmosis membranes. It's great for both short and long term PFAS compounds. The membrane size is small enough to physically exclude those compounds. But pre-treatment's very important so you don't foul the membranes. The design is based on the molecular weight cutoff of the membrane itself, and it's going to have the highest capital and life cycle cost that play into that. One of the issues with the membranes is you have a concentrate stream that can be anywhere from 5 to 25% of your total feed into the treatment system. So that liquid stream with PFAS in it can be troublesome to figure out how to dispose of that. Next slide, please, and I'll go for quicker after this. So with PFAS removal for Fluorosorb and the other adsorptive systems, typically there's a pre-filter on it just to remove particles larger than about 10 microns. And then we'll run through our filter system with a lead and a lag vessels on a skid or 2 skids. Very similar to how ATEC has been designing iron and manganese removal. We use sort of the same schematic for uranium and radium and arsenic and other things as well. Please go ahead. So again, I talked about sort of the small tank and the big tank approach with Fluorosorb and with anion exchange resins. We're talking about 2 to 4 minutes of empty bed contact time with a lead and a lag vessel that you can switch back and forth. With granular activated carbon, instead of 2 minutes of empty bed contact time, we're looking at about 10 minutes per vessel for lead and lag vessels. So they can be bigger equipment and a little more costly to put in initially as well. Go ahead to the next one. Some of the issues that have come up with people running these systems is with granular activated carbon. Some places have seen some biological growth in the granular activated carbon. So they can feed some chlorine into the system to help modify that or to mitigate that. The GAC will remove the chlorine, so you'll have to add it back again after the vessel, but that can help it. Typically with this kind of system, you got to have an initial backwash when you put it in or replace the media. It's a well-vetted technology. Media costs are pretty low, about $150 a cubic foot. They tend to be larger tanks, so they have a little higher initial cost and maybe life cycle costs as well. With ion exchange resins, typically not backwashed. There are lots of installations around. The resins need to get dissolved, so that can always be an issue to discuss about how that's going to get handled when it's time to replace those. There are some regeneration organic solvents that can be used, so that's a possibility, but those organic solvents need to be disposed of as well. Again, this is the smaller vessel price, smaller vessel approach, but the media costs can be pretty significant. So anywhere from $350 to upwards of $1,000 a cubic foot for a resin replacement. Fluorosorb, on the other hand, we've got the smaller system approach, so 2 to 4 minutes of empty bed contact time for ATEC. That's how we have been designing our iron and manganese facilities for 25 years. So we use that same platform. The cost approach that we have for Fluorosorb is almost the same as our iron and manganese costs for these treatment systems. So we can also do the media removal and disposal for these systems and typically have the lowest life cycle cost approach. Next slide, please. So just a quick preliminary comparison, granular activated carbon for a 1,000 gallon a minute system. Typically, these will be 12-foot diameter vessels. You'll have a lead and a lag vessel. We would look at an empty bed contact time over both vessels of 20 minutes. If we could get 80,000 bed volumes to break through, we could expect a runtime of 2,600 days. So over a 20-year period, that's only 3 changeouts. You can see the life cycle cost. That really benefits the life cycle cost of about $740,000 over that 20 years. With ion exchange, we have smaller tanks, two vessels, 10-foot diameter, a total of 550 cubic foot of resin, an empty bed contact time of 4 minutes between the lead and the lag tank. If we get 100,000 bed volumes, because we're running more bed volumes per day, it would need to be changed out every 685 days. So more change outs drives up the life cycle cost pretty significantly. With Fluorosorb, we would have smaller vessels that ATEC produces for iron and manganese, our same sort of platform there. We could get potentially a very long breakthrough of up to 320,000 bed volumes, which would give us a similar runtime to the granular activated carbon, looking at 3 changeouts over the life cycle cost. Our cost to treat a 1,000-gallon-a-minute well with the media in it is as low as $335,000. So low capital cost, low life cycle cost is really why we're excited about working with Setco and being able to provide Fluorosorb as a treatment option for PFAS. And these are ATEC's costs to put these type of systems in, but go ahead and flip to the next one. Other folks have independently looked at these costs. This is one for a treatment system in Arizona where Fluorosorb was the lowest life cycle cost. For that installation, you can go ahead and flip to another one. In Orange County, Jacobs has a well-researched, published study showing that Fluorosorb, again, lowest life cycle cost there. Go ahead and flip to the next one, please. And Colorado School of Mines also came up with an independent evaluation saying similar findings that Fluorosorb has the lowest life cycle cost as well. So please click the next one. ATEC provides these package skids. So we've have several of these systems in that have a lead lag configuration. They can run either side of the skid in a lead lag position, or we can provide 2 skids and run a lead skid and a lag skid and swap those around as well. We've got vessels ranging from 14 up to 48 inches in diameter. We can put up to 20 filters on a single train. In some cases more, but that's typically as large as we'll go. And we make our own vessels, which is a really, in California, a really key part of keeping the cost under control for us. So go ahead and flip to the next one. So just kind of a quick review here with ion exchange, very good for PFAS removal. The type of resin and how often you have to change it out are the key factors in the initial cost and the life cycle cost. So water quality makes a pretty big impact on ion exchange, but the type of resin is probably the number 1 factor to use. So testing up front is very important. Next one. With granular activated carbon, this is the big tank approach. Water quality is extremely important for how long granular activated carbon will last, as well as the type of PFAS compounds that you have in the water. Things like TOC or dissolved organic carbon can make a big impact in how long that granular activated carbon lasts and how quickly you need to change it out. And then lastly, the modified clay adsorbent, really there's some interesting research, pilot testing that shows, pretreatment certainly is needed, but in terms of water quality that fouls the resin, Dissolved organic carbon doesn't seem to have a huge impact on it. You can chlorinate through this media, so you don't have to worry about biofouling or some of the things that you get with the other media. And we don't have any reactions with the media like we would be concerned with chlorinating ion exchange resin. So replacement frequency is the big thing for Fluorosorb. And Setco, as Matt will tell you in a minute, they can do some modeling to predict the time. We can set up pilot testing, and we can do rapid small scale column testing as well to help identify how long the media will last between changeouts. Okay, next one. And I think we're going to turn it over to Matt here to talk about.
Yeah, great. Thank you, Lee. Very informative, and appreciate that summary at the end. With that, here I'll hand it over to Matt to go into a little more detail about the surface modified clay, aka Fluorosorb. So go ahead, Matt.
Thank you. Next slide, please. Okay, so here's what I hope to talk about today, an introduction to Fluorosorb. That's really the most important thing. I'm just making the assumption some of you on the call may have heard of Fluorosorb, but I'm going to go a little bit deeper, tell you what it is, where it's made, and we're going to review testing from McGill University. We're going to go over a case study from the Orange County Water District in Southern California. We'll look at some column work that was done by Colorado School of Mines. I shouldn't have left that in there. The University of Texas at Austin and injections with AST is part of a larger presentation wherein we include work that we do with Fluorosorb outside of water. So I won't be talking about that. Hopefully I'll leave some time for summary and questions. Next slide, please. Okay, so what is Fluorosorb? Well, I mentioned in the very beginning that the parent company, Minerals Technology, Inc., is a minerals mining company. And as such, they own a significant portion of the mineral rights to the bentonite that's in the Black Hills of Wyoming. And for over 80 years, Minerals Tech and its predecessors have been mining that bentonite and turning it into all manner of finished goods, like the ones I pointed out in the beginning, kitty litter, wine filtration. Well, Setco is a wholly owned subsidiary of MTI, and for 25 years, we've been mining that same bentonite and turning it into finished goods for environmental remediation. So think of organoclay MRM. So what Fluorosorb is simply the latest surface modification to our bentonite clay. This time the surface modification by our R&D group was specifically designed for the absorption of PFAS. And what you're looking at here are some of the grain sizes that we currently manufacture the Fluorosorb product in. If you take a look at the first line, Fluorosorb 100, you go down the column, you see we list physical properties there. But I would call your attention to that applications line at the bottom. So the Fluorosorb 100, a semi-powdered version of the product, is being used in situ stabilization and solidification. But for the folks on this call here, it's also being used in diffusive air filtration treatment systems. The next column over is Fluorosorb 200, which is the next grain size up. Again, we list physical properties. This is being used for pump and treat, permeable reactive barriers, and in situ stabilization. Next is Fluorosorb 300. I won't go over that today because it's not germane, but suffice it to say, Fluorosorb 300 is simply Fluorosorb mixed with anthracite that we thought we might need in mixed waste streams that have a real high oil content. Next, we have Fluorosorb 400. It too is being used, one of the larger grain sizes. It's being used in pump and treat and permeable reactive barriers. So you may notice we said pump and treat for 400 and for 200. The reason for that is 200 is what we recommend for drinking water and cleanish groundwater inputs. Fluorosorb 400 is being used in surface water plants and pump and treat facilities. I should mention before I go to the next slide, not pictured here, to the right of the Fluorosorb 400, we now have Fluorosorb 600, the largest grain size we're manufacturing, and that's being trialed in surface water plants as well. And to the left, we also have Fluorosorb P, a fully powdered version of the product, which is currently being injected for upgradient source control. Next slide, please. So again, today we're going to be concentrating on the work that we're doing with Fluorosorb around water, but is important, I think, to mention that it's very versatile in its ability to be deployed. It can be used for groundwater, for drinking water, because it's NSF certified, pre or post treatment, and sediment capping. I won't go into that too deeply other than to say, if you look at that picture on the right, the cutout there shows what's called a reactive core mat, and that's two needle punch geotextile fabrics that hold in place a known quantity of Fluorosorb, and we have deployed that on several surface water remediation sites. So as I go through this part of the presentation, we'll show you how Fluorosorb outperforms other products with higher absorption kinetics, better absorption capacity, and very importantly, less effect from competitive absorption. And it can be used in conjunction with other products. It is fully commercialized. All the lab and field pilot tests are complete, and it was formally launched as a product in May of 2019. Next slide, please. So again, just to reiterate, we're going to go over some testing. We're going to look at isotherm testing, take a look at some of the absorption kinetics, absorption coefficients, absorption capacity, and we're going to compare to the medias that have already been discussed thus far, namely GAC, IX resin, and we also have a comparison to biochar. Then we'll cover that Orange County Water District case study, go into the McGill column testing work, which was work to show Fluorosorb in conjunction with other products, and we will not be doing the soil amendment section. Next slide, please. Okay, we start with McGill University up there in Quebec, Canada. And what you're looking at here is actually some soil work we had them do. We sent them 4 different DOD soils, 2 from Canada, 1 from the US, and we had them mix our semi-powdered version in with the goal to just see how much we could reduce leaching. Again, for this group, I'm not going to go over this, but I left this slide in for a particular reason. I wanted to use it to, if you will, set ground rules for the rest of the slides. And what I mean by that is if you take a look at the column on the right and look at the top, you'll see that what McGill studied was 49 different PFAS. And as I go through the rest of this presentation, as you can imagine, I won't be discussing the data on all 49 of those because we'd be here a long time. But so I'll be presenting data on PFOS, PFOA, and a couple other potentially or regulated compounds. But I wanted to let you know that if for whatever reason you have a customer or you have a site that's driven by one of the other PFASs, we likely have the data and we can do the modeling necessary. Having said that, next slide, we'll get into what the main work that McGill did for us. And that was this comparison of Fluorosorb to GAC, hardwood biochar, and ion exchange resins. Next slide, please. You could see that in this groundwater experiment, for PFOA, PFOS, and total PFAS, Fluorosorb significantly outperformed granular activated carbon and biochar and performed similarly to ion exchange resin when you're looking at removal efficiency as the parameter. Now, what should be mentioned here is while it performs similarly to ion exchange resin, and emphasizing what Lee has already mentioned, you're getting similar removal efficiency, but all of our reconnaissance tells us that the cost of the media is anywhere from a half to a third of that of the IX resin. If you take a look at that, well, one more thing on that side. If you take a look at that box on the top right, that is a description of the experiment that was done where 40 milligrams of absorbent was placed into 500 milliliters of Air Force-based groundwater, and the test was taken out to a 7-day equilibrium. That's going to be important, that 7-day equilibrium part, when we get to the unique absorption mechanism that Fluorosorb has, and I'll do that in just a few slides. Next slide, please. So I mentioned just a moment ago that the effect of co-contaminants is very important in Fluorosorb's ability to uptake PFAS. And what we had McGill do for us is spike the samples with the co-contaminants you see listed here to include naturally occurring organic matter at a very high dosing, higher than you would normally see on a given site. They also spiked with diesel, 1,4-dioxane, BTEX, and TCE. And you could see, except for about a 30% reduction in removal efficiency for PFOA in the presence of high NOM, and about an 18% reduction in removal efficiency for PFOS, again in the presence of high NOM, there was virtually no impact to PFAS's ability to, Fluorosorb's ability to uptake PFAS in the presence of these other co-contaminants. And if I could ask you, Steve, to go backwards just one for a second. Again, take a look at, this is with no co-contaminants. The removal efficiency for PFAS was about 89%. Next slide. Take a look at the removal efficiency for PFOA in the presence of diesel, the darkest gray bar. It goes up to 96%. Now, we're not implying that we should be adding diesel to any of our sites, but this increase in PFAS removal is likely due to this unique absorption mechanism that I'll cover in just a little bit. Next slide, please. Finally, when we were working with McGill, we've known, because I mentioned we've worked with these clays for years and years, we've known that they have an immense surface area. But that doesn't mean much if you can't take full advantage of it. So what we wanted to do was create an unusually high driving force. So what we did is we super saturated the samples with the PFAS you see listed here. And the idea here was to see, let's how much we could load on to our media. And what we found is we got anywhere from 14 milligrams per gram for PFHXS all the way up to 31 milligrams per gram for PFOS. So that had us knowing we were on the right track. We're not implying that you would get those type of absorptions in the field because you're not going to have the false super high driving force, but we do have a lot of room and it is proving to be very absorptive. Next slide, please. So McGill concluded that Fluorosorb is highly effective in removing PFAS from real-world impacted groundwater, superior to GAC and biochar, and comparable to ion exchange resin for most PFAS. And it's also proven to be effective in mixed waste groundwater conditions. Next slide, please. Okay, now we move on to this case study of the largest drinking water pilot done in North America, and it was done by the Orange County Water District. Orange County Water District is a shared services group for 12 water producers in Southern California. And back in, I think it was 18, they knew that state level PFAS MCLs were coming. So on behalf of their member clients, they wanted to do the largest pilot they could do. So what they did is they went out and got some water from the well you see pictured on the lower right, a production well called the Bessie well. They measured for the two soon-to-be regulated PFASs, and you can see they got up to 23 PPT PFOA and up to 27 PFOS. Next slide, please. This is the water quality from the Bessie well water, and you can see that there's not much to worry about. There's not high nitrates or chlorides. But what I would point out, if you look at the TOC, it's at 1.5 milligrams per liter. That and much higher is not a problem for Fluorosorb. However, not in what we're going to discuss here, but a separate study by Orange County Water District looked at the TOC on all 12 water producers and tried to determine at what point does TOC negatively impact carbon. And as it turns out, right at about 1.5 milligrams per liter, as it gets higher, you start to see some degradation in PFAS absorption with carbon. Next slide, please. So what Orange County wanted to do was get their hands on every available absorptive media at the time, commercially available. So they went out and got 8 different GACs, 4 different ion exchange resins, and 2 products they referred to as novel absorbents. They got the Setco product, the Fluorosorb, and another product, which was a cyclodextrin product. Their plan was to start with RSSCTs just to get some differentiation between the products. And regardless of the results of those rapid small-scale column tests, they were going to go into the field in these full-scale columns you see pictured here, which is what they did. So in setting up the empty bed contact, setting up the RSSCTs, they went to all the manufacturers and said, what do you need for empty bed contact time? All the GACs wanted 10 minutes. The ion exchange resins wanted 2 minutes. The other novel absorbent needed 5, and the Setco needed 2 minutes. Next slide, please. Now, what we're looking at here are the results of those initial RSSCT tests. And as I go through this, you'll notice that there's no results for ion exchange resin, and that's because at the time, ion exchange resin manufacturers would not allow their product to be ground to do an RSSCT. I believe that's since changed, but here's the results that Orange County did get. Up at the top, next slide, please. You can see these are the results of the GAC RSSCTs. And they set their action level at 8 PPT PFOA, which was 80% of their reporting value. You can see that red bar at the bottom. That's the best performing GAC, something they called bituminous GAC number 2B. And we see that it broke through at the action level at about 60,000 bed volumes. Down the bottom are the results of two different RSSCTs run on the Fluorosorb product. The blue dot was run by Colorado School of Mines at just over 3 minutes, and the red square was run by Battelle at 1 minute. If you take a look at the blue dot, the School of Mines work, you see that there was no breakthrough above the action level until over 600,000 bed volumes. And if you take a look at the red square, you see that it got to about 580,000 bed volumes and never broke through. That's not because it never broke through. That's because that's the point at which COVID hit and Battelle had to leave the lab. Once Battelle could go back into the lab, they reran the RSSCT on the Setco product at 2 minutes. And once again, it was over 600,000 bed volumes to the breakthrough. So the best performing carbon, 60,000, the best performing, and the Fluorosorb product, 600,000. And if you factor in the difference in the empty bed contact times, it's approximately a 5 times greater lifespan for the Fluorosorb product, which is what we've seen in all head-to-heads. Next slide, please. So this is from the Orange County Water District's final report that they published after all the work was done. You could see that all the bituminous GACs broke through earlier than the Fluorosorb, all the non-bituminous GACs. All but one of the ion exchange resins broke through well before the Setco product. And on the far right is that other novel absorbent. It broke through earliest of all. Next slide, please. Again, from the Orange County Water District final report, verbatim, they said Fluorosorb 200 absorbent showed the latest initial breakthrough of all 14 medias tested with an empty bed contact time and footprint akin to that of ion exchange resins. Next slide, please. Okay, we move on to work that was done by the Colorado School of Mines. And I should mention that this presentation is not really in chronological order. In fact, this is some of the very first work we did as we were developing the product. Because at the time, we weren't sure where we could fall in the marketplace. We thought it would be a good idea to get some data around if you put Fluorosorb in front of GAC or IX, how much longer could you have it last and what was the value proposition there? So with that in mind, we went to the School of Mines and they set up 4 columns in lead lag, as you see pictured here, with the first being Fluorosorb followed by Fluorosorb, then GAC followed by GAC, then Fluorosorb followed by GAC, and lastly, Fluorosorb followed by ion exchange resin. Next slide, please. This was a military site, so next slide. The action level was set at the health action level at the time, and what we're looking at here is the breakthrough of the lead carbon vessel is the gray dot, breakthrough at their action level, and the green diamonds is the breakthrough of the lead Fluorosorb vessel. So we see that the lead carbon vessels broke through at about 2,000 bed volumes, and the lead Fluorosorb broke through at about 8,000. So at this point, early on, we started to see this in all comparisons, anywhere from 3 to 5 times greater bed life as compared to carbon, similar bed life as compared to ion exchange resin. And so we said, okay, we're going to go, we will, on some sites, we know we're going to have to be in combination with others, but we started to develop the product as a standalone. Next slide, please. So why is it that we're getting this superior absorption, bed life, et cetera? Well, there's lots of reasons, but I've alluded to it a few times now. One of the main reasons is a very unique absorption mechanism. And this slide is here to help me describe what that is. If you look at the top, that's what a typical isotherm curve looks like when we do our studies. Every one of them that we've done had this inflection point, an odd shape to the curve. And we had a theory of why that was, and we've since gone and proven it. And those 2 images on the bottom can help me explain. So on the left, what you're looking at is what the Fluorosorb platelets look like after we do the surface modification to the bentonite clay. The platelets stack up on top of each other like a deck of cards, and there's a space in between that's referred to as the D spacing. Now, again, we've known forever that there's a lot of surface area, so much so that if you could pull these platelets apart and lay them side to side and end to end, 1 teaspoon of this product would have over a football field of surface area. But again, surface area doesn't mean much if you can't take full advantage of it. So what we did is we measured the distance in that D spacing prior to the inflection point that you see up in the top of that isotherm. Next slide, please. Next slide. And then we allowed more PFAS to enter the system, got past what we believed to be the inflection point, and then we measured that D spacing again. And the results were Before the inflection point, the despacing was 25 angstroms, and after it was 50 angstroms. Unless we worry, as I did when I first heard this, that sounds like swell, this is happening on the micro level, and we now know with full-scale running systems that there's no swell in the macro level, no pressure drop loss. It flows fine. However, this expansion of the platelets allows more PFAS to get in once the initial adsorption has happened. So the PFAS gets in there, coats all the surfaces in the gallery, it begins to open up, and then the PFAS is attracted to itself and it forms these hemimicelles, pulling more PFAS in. Now, if you remember just a moment ago, I said we actually absorb more PFAS in the presence of diesel. This is likely due to the same phenomenon where the diesel is attracted into those galleries. It's a fairly large molecule. It also opens up and allows more PFAS to get in. So this unique absorption mechanism is proving out to be effective out in the field in the real world. Next slide, please. So here's just a list of some of the published papers. It's by no means comprehensive. It seems like weekly now there's another paper coming out. I believe this presentation will become available to everyone, and you can read up on these papers if you're so inclined. Next slide, please. And this is wrapping up where we are, and again, just for drinking water. There are 8 drinking water sites contracted, awarded and contracted. The 4 on the top are ones that are currently pumping, and the 4 on the bottom should be constructed and running all within the first quarter of next year. Next slide, please. So Fluorosorb is no longer in the pilot phase, although we know for drinking water we're going to have to pilot. It's fully commercialized. It's manufactured in our ISO 9001 certified production plant here in the US, NSF certified, and there's no limit to the capacity of what we could make, to satisfy the market's needs as the market's needs grow. One of the reasons I say that is we have an idled plant in Europe that, if the market continues to grow, we can start that up in short order. Next slide, please. That's it on the deep dive into Fluorosorb, and I hope I left some time for questions. Looks like there's a little bit of time left. I'm happy to see what was asked.
You did not. Thank you very much. And I'll ask Lee to come back on camera. And I've got a few questions here that we'll go through. And just a quick note that as far as testing of Fluorosorb goes, ATEC is able to either test on site as a pilot, or we can conduct RSSCT testing. RSSCT is typically much more cost-effective due to the cost of actually testing for the PFAS inlet and outlet. Those are very expensive tests, so that tends to be more cost-effective. Matt, like he just said, right? He's providing the media to do these tests. They're interested to get their product in consideration, and it is very subjective, as Lee pointed out. There's a lot of factors, right? Short chain, long chain. Each site is going to be subjective, so it's important to do a good analysis, right? Look at each option that is potential. Obviously, there's a lot of good data here showing that as you dive further into that life cycle cost analysis, Fluorosorb is really proving itself out. So we're happy to engage with anybody to help analyze this. So with that, first question we got here are anonymous speakers are talking about removing PFAS from groundwater. What about surface water sources that are replenished by rainfall runoff? Yes, we would be able to equally address both surface water as well as groundwater. I think the key difference there is that surface water is typically going to require a lot more pre-treatments, whereas groundwater oftentimes, is pure enough, besides the PFAS and a few other things, that you could go direct to these absorptive technologies that we've been reviewing here today. Lee or Matt, anything to add there?
I'd just say, Matt went over the different products you use for surface water. Typically, if we're removing PFAS from a surface water, it's going to be a post-filter contactor. So very similar. We've got one GAC application. We just won. We certainly could do it with Fluorosorb as well.
Sure.
The only thing I would add to that is we're about a year and a half into a lot of different pilots on the big gravity contactors at the large surface water plants. It looks like first quarter of next year, two of them are going to, one of them is going to put in 100% Fluorosorb 600 into one of their contactors because they found that the Fluorosorb 600 was sufficient for the turbidity and the normal things that they're looking at, as well as reducing the PFAS. Now, as you go larger in grain size with Fluorosorb, you start to lose some of its absorptive capacity. So that's one surface water plant we're working on. The other one is using Fluorosorb 400 again in the first quarter, and what they're going to do is put 6 to 12 inches in these big gravity contactors of Fluorosorb, and then the normal 7 or 8 feet of carbon on top of it. So that's sort of like a stay tuned thing. In the columns, it has worked, but these are gigantic contactors, and as we get more info, we will be hopefully telling everybody good news.
Great, thank you. Second question we got was, will copy of slides be available? Our intention is this webinar has been recorded, so we will place this on the ATEC website, but we would not be sharing the slides. But if you watch the video, right, you can extract that. So next question comes from Genevieve. My apologies if I did not pronounce that correctly. Genevieve Rankin. Do we know if incineration of residuals completely breaks down the PFAS chains? What happens to the residuals that are landfilled? With the PFAS entering the environment again as the landfill media break down? Clarifying in the question, thinking long term here, 50 to 100 plus years down the road. So I'll take the first pass at this, essentially to say that when it comes to landfilling, the answer is it depends. There is a test that needs to be done to see about what it takes to desorb that off the ion exchange or the Fluorosorb. I think the initial results are showing that Fluorosorb holds the PFAS quite tightly. It is not expected to desorb in landfill conditions. That's not necessarily true for ion exchange. The incineration aspect is, I think that's specific to GAC. So I'll turn it over here to Lee and Matt to add to that.
Yeah, I would say the destruction of PFAS compounds is tightly tied to the temperature that they incinerate at. So it takes a pretty high temperature to be able to actually destroy the compounds.
Yeah.
But there are places that can do that.
The only thing I would add to that is I don't have any hard and fast facts, but the scuttlebutt, if you will, is that incineration is absolutely approved currently, and it's defined, as Lee said, at has to be at a certain temperature. But there's still investigations going on. The commercial incinerators are in the process of showing that there's complete destruction and nothing's coming out of the stacks. And for all I know, they've completed that and we're good. But last I heard, that was in process. And with respect to landfilling, I can only speak to Fluorosorb, but at the Setco in a different division has been working with landfill companies for 30 years. And one of those landfill companies came to us and said, we would like you to run leaching tests on your spent media. At the time, the only spent media we had was from a landfill leachate project. So consider that worst case scenario. Very high concentration of PFAS plus all kinds of other stuff in there. So we took our spent media after a change out and we ran TCLP testing, SPLP testing, and the leaf method, the leaf leaching method. And the results were, except for some minor hits on some of the shorter chains, we were ND on all the regulated compounds. So that has been beneficial to us when people are thinking about using Fluorosorb in the ground for stabilization. It may someday be helpful for land approval to landfill, maybe at a subtitle D landfill. But right now, nobody knows because the actual landfill final regulations haven't been written. So I hope that helps.
Great, thank you, Matt. The next question comes from Mike McKell Foltmar. He states that rural Alaska has a lot of smaller airports with PFAS contamination, some of which impact residential water wells. These communities often lack adequate landfills. Are there restrictions on where potentially PFAS contaminated materials from water treatment can be landfilled? Short answer there is yes. It's subjective to each state and it's subjective to the media. Typically what we're hearing is that ion exchange media has to go to a PFAS approved, a hazardous waste approved landfill, whereas FluoroSorb could go to a standard landfill. Anything to add there, Matt or Lee?
It's everything's up in the air till they write regulations. So generators are just making the best decisions that they can. I've actually talked to a few generators that went to a subtitle Title D because by law they can at this point. But by and large, most are just going to a recreational hazardous waste landfill or an incinerator. That's the most common practices currently.
All right. Matt, this is a question I think for you. It's quite specific. John Liberzon asks, has FluoroSorb ever been used or tested to polish PFAS from foam fractionation underflow coming from landfill leachate treatment systems? What is the max concentration of influent PFAS that FluoroSorb can process while guaranteeing a non-detect effluent concentration on EPA 1633?
Okay, a little bit to unpack there, and it's a interesting answer, I think. Two things are going on. There's a pilot that's going to start up in another couple of weeks. It's all designed, wherein the foamate, after it settles, is going to be run through a vessel and then recirculated, and we're going to see what comes out the other end. And at some point, it's going to go, the effluent from this recirculation through FluoroSorb is going to go back into the beginning of the system and back through the foam fractionation unit. That's one thing. On another site, there's pilots going on where they're contemplating using FluoroSorb as a sink for the foamate. So the plan is pour the foamate into a half a drum of FluoroSorb or whatever the quantities are, and then put some Portland cement in it and send it back to the landfill. That's as far as we've gotten with any connection to or working with foam fractionation. We're in conversations with people who are looking at, I don't know if I fully understand this. So you've got the foamate, which is the super concentrated foam that needs to be dealt with, but there's, I think, sometimes residual in the filtrate. And there's a couple people who are starting pilots on sending the filtrate through the FluoroSorb as a polish. But there's no empirical data yet because it's all, relatively new. I hope that answered.
Yeah, very good, Matt. Thank you. So we're down to just a few minutes here. I'm going to pick up a couple questions. Susan Rocha asks, our Smart Water Co. needs filtration for iron and manganese. Is that a simpler system since we do not believe we have any PFAS issues? Yes, that is. I wouldn't say simpler. It's a different system. It's application specific. ATEC can help with that. PFAS would typically be treated after iron and manganese, but in your case, it sounds like you don't have that issue. So please reach out. We can help you with that. Another anonymous question for clients that use ATEC filters for iron and manganese removal. Would additional contactors be required to remove PFAS, or could FluoroSorb be used to remove iron and manganese and PFAS? Is there higher head loss through FluoroSorb compared with iron and manganese removal media? So the answer there is that yes, additional contactors are needed. We would first pre-treat for iron and manganese. Otherwise, that can potentially foul your absorbent media, whether that's GAC, in exchange, or FluoroSorb. So we would first remove the iron and manganese, then have your contactors for the absorptive treatments. As far as head loss goes, I think it would be similar. Lee, can you help me out there? Would there be a difference between iron and manganese head loss versus fluorospore?
It depends on which media we use, but Matt, I think we're still looking at 2 to 3 psi of head loss typically through a bed.
That is correct.
Great. So we're at time, but there are some other good questions in here. Let me just pick on a couple. If anybody chooses to jump off, we do appreciate you attending. I'll advance this slide here. This is our contact info for each of us. If you would like to reach out with any follow-up questions, or if we didn't get to your question here, please do reach out. And again, we tend to post a recording of this webinar to our website. And thank you everybody for attending. So here's a couple other questions. Got a good one here from Christopher Keenan. We mentioned that TOC greater than 1.5 milligrams per liter can reduce PFAS removal performance. The question is by how much, and is TOC being removed by fluorospore?
TOC is not being removed from Fluorosorb. It largely ignores it. I don't know the specific numbers on the reduction. However, the paper that I was referring to is by Greco et al. So I think if you just went to the Orange County Water District's website, they have a link to all of the papers that came out of this study, and look for the one that says Greco et al. It might be titled TOC impact to carbon.
Yeah, I think that's correct, Matt. And I believe the spelling there is GRECO, was one of those lead authors.
Yeah, GRIECO.
IECO, okay,
Mm-hmm.
great. David Mustonen asks, is fluorosorb applicable for industrial wastewater treatments for PFAS removal containing elevated TDS, which is approximately 3,000 to 5,000 ppm TDS?
We are working on wastewater plants, but TDS at that level there would have to be pre-treatment. I think TDS for any flow-through media up around that range is likely going to be problematic. The benefit of in wastewater, the benefit of fluorosorb is more about ignoring DOC, TOC, solvents. All of that will go right through, not impact the fluorosorb. But I think TDS would be problematic.
It looked like, Matt, I saw one test result that showed high calcium wasn't an impact with fluorosorb either. So is it something else?
Yeah, better stated, it should be, it depends on what the TDS is.
Okay.
And you know what I would suggest, if you want, you could call the number you see listed there, get the exact water quality data over to us. As Lee alluded to, we have a model where we input the water quality, the PFAS concentration, and we can make some predictions on bed life.
Great, great. Anonymous attendee asks, have you done any full-scale exchanges yet? Matt, I know you've got a few of those on the East Coast, but I imagine those are not to that point yet.
Meaning full-scale changeouts, right?
Correct.
Yeah. We've done a bunch at say vessels that are 6 foot and under diameter. We've got a 1 MGD site that's been running for about 1.5 years now. Only one change out, but I guess the reason for the question, if I'm reading into it correctly, is so it was loaded without any issues pneumatically or hydraulically through a slurry truck, and then it was removed through a slurry truck without issue in or out.
Excellent. Okay. Let's see here. Here's a question, Matt, that you would like probably field. This comes from Mikkel Fultnar. He wonders if fluorosorb is going to be scaled down to meet residential demand. if there's any plans to create a residential type of product.
Not by Setco. And what I mean by that is that's, we're not in that business per se, but there are two large OEM companies that have signed NDAs with us, not commercial agreements, just allowing them to do the research. As I understand it, our NSF doesn't apply to their point of entry and point of view systems. So I don't know how far along they are, but they were in the process of using the Setco media to get the whatever kind of NSF you need for poets and point of use. And someday maybe in the Home Depot.
Yeah. And I would say from a Setco, or sorry, from an ATEC standpoint, we scale down to about 10 gallons a minute. So residential demand, I think, is relative to how much of a water conserver you are, or may not be. So food for thought there.
I don't want to elaborate too much on it, but it kind of gives you a feel for where we're at on it. We've had lots and lots of calls from independent contractors who put home use systems in, and they tell us about their design. We're sure it'll work, but we refuse to sell it to them because our biggest worry is if you're relying on the homeowner, we can give you a predictive model, but if you're relying on the homeowner to change out on time, we're too much of a conservative company to do that. We're willing to work with these OEMs because it's going to be we will just be a component part of their product.
Okay. So I think there's two more good questions here. We've still got a pretty good amount of people on. So let's go ahead and wrap these up. This one I think is just further clarification of what happens to the media once it goes to a landfill. So Jeff Tassoff asks, what are the liability concerns with disposing of this media in a landfill? Have any leachate studies been performed? So Matt, can you just talk everybody through what you have done in that regard?
Yeah, I can tell you what I know, but Setco's a media manufacturer only, and we rely on our partners such as ATEC to handle the disposal. And even having said that, the liability will always remain with the generator due to RCRA regulations. So having said all that, I mentioned earlier, we've done leachate testing, all variety, on a spent landfill leachate media. We're in the process of doing the same thing on drinking water, which presumably will be even better leaching results. So we've established that there's very little leaching or no leaching of the regulated compounds out of the spent fluorosorb. The liability is a question probably beyond my legal expertise. Suffice it to say that the landfill companies, at least the ones that I used to work for, will say that they'll take title to your waste, and they will, but if they go Superfund, it's cradle to grave laws, right? So the generator will always be responsible. And again, I don't want to wax philosophically too much here, but for 30 years, if you have hazardous lead waste and you can prove that you've stabilized it, and in that case, the proof is doing a TCLP test. If you can take hazardous soil that's hazardous for lead, stabilize it with some reagent, do a TCLP, and it's under 5 parts per million, you can send it by law to a non-haz landfill. Now, when they get done writing all the regulations on PFAS, I don't know why they couldn't do the same thing. They have to, do some vetting of what will be the appropriate test that gives us comfort that we can do it. But I really believe that at some point, whoever's media can hang on to the PFAS as proven by whatever test they choose, they're going to be able to go to a subtitle D. If they can't, the expense and the capacity in the nation of hazardous waste landfills could be sorely tested.
Great. Thank you, Matt. Lee, anything to add?
I mean, there's research underway with ion exchange resin and with fluorosorb, looking at desorbing the compounds off the media. for a different way of disposing of it. So I think, you know, in the near future, we'll see some different commercial options available for disposal.
Yeah.
Yeah, we're deep into the R&D for cleaning the PFAS off of our media with a solvent rinse, just same as everybody else. And then you'd have a concentrated liquor that either gets well, I guess incinerated would be the only choice then.
Great. And we've supported a couple of consulting engineers looking at this. I think it's subjective, right? They've come up with different conclusions about which adsorbent material can go to which type of landfill. So they've analyzed that, you know, specific to each site that they've put together a design for. And that's part of that life cycle cost, right? Because you've got a trucking cost that's different, whether it's a standard landfill versus perhaps a hazardous waste landfill. So it's just one of these things where you've got to look at what's permitted right now. That's what I have to make my decision on. Okay, let's research that. Let's figure out what that real cost is. Last but not least here, question getting more into the surface water treatment as well. This is from an anonymous attendee. Has there been any studies on replacing anthracite with fluorosorb in gravity filters? Would the fluorosorb 400 be the recommended product for such an application? Matt, I think you can just kind of reiterate what you said earlier. There is a study that you're about to kick off, right?
Yeah, we've been on a study for a year and a half now, and it looks like it's been in columns. And the product they tried was Fluorosorb 600, the largest grain size we make. And they got, in the last report, they got sufficient PFAS removal, but also the turbidity reduction that anthracite was producing. So late spring, supposedly, we'll be filling up one of the gravity compactors with Fluorosorb 600. And no anthracite, no other products in there, to see how it performs in full scale.
Great. Well, that's all the questions that I think are relevant here. I really appreciate Matt and Lee, your support here of the webinar, and everybody that attended. So feel free to reach out to us, and thanks for coming today.
Thank you, everyone.
Thank
Bye.
you.